Okay, first of all, thank you for this invitation. It will be a wonderful day. My talk is about adaptive practice and monitoring systems for education and research. And this is something I started about 7 years ago. And I will try to explain how we did this and why we did this and what we do with it. I'm not an educational researcher at all. I'm a professor of psychological methods, and I have an interest in developmental science, quite theoretical. So my main research interest is formalizing psychological science, making formal mathematical models, simulation models. And in the past I did lots of work in the area of developmental science from a complex system perspective. Important papers are mentioned here, a paper on cognitive transitions, and more recently a paper on a network model for general intelligence. And this is one chapter that summarizes most of this work. And yeah, if you are interested in complex systems, and many people in science are, then one important point is that measurement is important. So that brings me back to my original field, psychological methods and measurement. If you want to study complex systems like the climate or ecosystems or financial markets, or there are many more examples, then we need really high, frequent, valid and reliable measurements. So at some point for some project about 8 years ago, I decided that we needed daily measurements of what children do in schools in terms of learning language, math and cognitive development. But testing daily in schools, that's quite impossible. This is in Dutch, but this is one of our political parties that says stop testing terror with little children. So that's quite a topic, and I guess it's everywhere the same. It's impossible to go to schools and do a formal test every day. So we had to find a solution, and the trick is to realize that children do practice every day math and language, and if you can just tap this info from the daily practicing, we have info about what they do daily. So we decided to make an environment, a website, where they can do their daily practicing in such a way that's interesting for them, but also that we can collect data on what's happening in development. And we added some other ideas. I have no time to go over all these ideas, but one is the idea that reading, writing, and arithmetic are also instances of expertise learning, and that we need deliberate practice there. There are large individual differences in elementary school children, and it's really interesting to use adaptive learning methods so that every child can work at its own level. And of course, if we do these automatically on the computer, on a website, teachers don't have to check all the exercises. We can do this automatically. We can provide them with all kinds of learning analytics. And lastly, yeah, we can use the data for scientific research. So we decided to build such a system, and we started with the idea from psychometrics. In psychometrics, there's a certain idea that's called computer adaptive testing, or computerized adaptive testing, I have to say. Computerized adaptive testing is quite a simple idea. If you do a test or an exam, you have to do all the items. You have to you start at 1 and that can take 1 hour, 2 hours, or 3 hours. But a smarter way is to do it like this. Whenever you solve a simple item, you can get a more difficult item. If you solve that item again, you get a more difficult item, etc. But if you fail an item, you get an easier item, and ideally in just a few items you find the position on the ability scale where the child is. Of course, that's much more noisy in reality, so there's more error in this process. But in this way, you do not have to make the whole test, but you can quickly find the position on the ability scales with less items than in a normal test. That's the idea of computerized testing. And we want to adapt this. We try to adapt this idea to computer adaptive practicing. But there are two problems using this approach. The first is that you need to know all the difficulties of the items. That's basically, this is called an item bank, so normally there are about a few hundred items, or maybe a few thousand items. So you need to have the difficulties. And the other point is that in choosing the next item, this is working optimally if the next item has an estimated expected probability of 0.5. And this means that in a computer adaptive test, you fail about 50% of the items. That might be good in testing, but that's not good in practicing. So there are two problems are these. You have to know the difficulties of the items. That requires pre-testing. Pre-testing is very expensive. And if you set the probability correct, expected probability correct on 0.5, children will quickly leave the system. They hate to make mistakes. If they make mistakes 50% of the time, they will just quit the whole system. Of course, you can select easier items. We can easily take items for which the expected probability correct is higher, say 0.75. But then the advantages of cut, that you quickly find the position on the scale, diminish. Now, we solve these two problems in two ways. First, the pre-testing problem. We borrowed a system from sports, chess. I don't know whether any chess players in the public here, but in chess they have rating systems. And they are beautiful systems. And the whole idea of these rating systems is that you can just have a lot of people. We can all go play chess or whatever game here. And you can use the ELO system to compute abilities. And the whole idea is that if Rob and me play a game of chess and he wins, his rating will increase a little bit and my rating decreases a little bit. And how much this increase and decrease is depends on our starting rating. So if my rating was much better than Rob's and I will lose lots of points and you will win a lot of points. That's basically the whole idea. It's easy to put that in equations. I don't show you the equations. But the trick is that we can just start with it. We can give everybody a rating of 0 or 1,000 or whatever. And we can just play this whole system. And then all the ratings will stabilize after some time. So you don't need pre-tested or initial ratings. You can just start with arbitrary ratings. And this whole system will stabilize. And that's what we do. Of course, children don't play math games against each other. They play against items. So a child gets, say, 6 times 6. If he succeeds the items, solve the item, then the child will increase his rating and the item will decrease its rating. And the other way around. And that's what's happening in our system. So in our system, we can just start with students and items, let it go, and then quite quickly, at this time, we have so many players that now just in a few days, the whole system stabilizes to the difficulty and item ability ratings that you are looking for. So this is a self-organizing testing system. The second point, are the equations. I put them on the slides, but I'm not going to explain every slide. It's important to know for people that know something about item response modeling, that mathematically, this ELO system is equivalent to the famous Rush model, the most basic IRT model in the psychometrics. Now, this is an example of what's happening, and it's also quite interesting. And so these are just items in one of our game, the addition game, and after some time, the ratings appear to be this. So this is the order of items in our system. And that's quite interesting because, as you see, 2 plus 2 is the easiest item. That's easy. But then 80 plus 10 or 44 plus 3 are easier than 8 plus 9. And at least in the Dutch educational system, 8 plus 9 is much earlier taught than 80 plus 10. That's a 2-year difference, I think. But in our system, it easily shows that 80 plus 10 is much simpler than 8 plus 9. So this is one of the things that happen. The second point was about this 0.5, that the computer adaptive test works with the expected probability of 0.5. If you do easier items, then the cut is not working anymore. Our trick is to use response times. So we look at response times. So we can. The idea is that we can give you all easy items, and you will all. I can all ask you all 6 times 6. You probably all know 6 times 6. But still, I can find individual differences in the response times. And I can use the response times as input for the system. That's what we do. And we use a certain trick for that. We use a scoring rule. We think it's important that children know how speed and accuracy are weighted. This is a speed-accuracy trade-off, a very important idea. And we use a scoring rule for this, and the scoring rule stated here. It says that you have some time for the item, say 20 seconds, and your score is the remaining time. So if you solve the item in 5 seconds, you get 15 points. But if you fail the item in 12 seconds, then you lose 8 points. That sounds maybe a little bit complicated, but we easily visualize this. For every item, they have coins. They can win these coins, and every second, one coin disappears. And if they give a correct answer, they turn green. Okay, that was too hard for my PowerPoint ability, so that's not there. But then they turn green, they get these coins. They go to a money bag, and they can buy virtual prizes with it. And if they fail, they turn red, and they lose these coins. So that's an easy visualization of this rule. And again, this has very interesting statistical properties described in this paper. So, yeah, we have a new computer adaptive testing system, which I call computer adaptive practicing system, which is based on this ELO system. And it's an extended ELO system because we also use the response time, so it's a little bit more complicated. And we have these scoring rules. And in this way, we don't need pre-testing of items, which, as I said, is incredibly expensive. And we can allow for easy items, which is important in practicing system. So that's the psychometric statistical background of our system. Now, the second thing is to just build the system. And for this, we have developed a website, and it's called Maas Garden. Actually, it's called Rekentuin, but that's Dutch. We have a Dutch version and an English version. The Dutch version is very popular, the English version not, but it's still there. So you can look it up, you can try it, you can do a demo. It's called maasgarden.com. And the whole idea is that children log in with their own password, and then they go to this website and they have a garden. And the garden have plants. And if they have to keep their plants healthy, and they can grow if their rating goes up. And if they click on one of the plants, they get a game. And these games are really simple. This is just a game, so this is just a subtraction game. You just get an item. So games a bit hard, a bit overstated, but I must say they see it as games. And we started with just 4 games: multiplication, addition, subtraction, and division. But nowadays we have lots of games in this system. So counting for younger children, series, numbers, main operations, but also fractions, clock reading, but also some IQ-related tasks like working memory. This is the famous set game. This is about deductive reasoning. So we add more and more games. In principle, we can put any game in there for which we can build a large item database with a huge variation in ability of a difficulty, and which can be scored automatically. And this is it for children. For teachers, it's looking like this. So teachers can go to log into the site, and they go to the back end, and then they can get all kinds of learning analytics. So for instance, this is an overview for the class. So these are all the children here. These are all the games, and then there are some color scheme which says that red, of course, not good. So you can easily see that player 5 has some problem in the basic arithmetic abilities. But it could also be the case that maybe the whole column of division is red, so the whole class has a problem with division, and then it might be time for some change in the curriculum. And it's all relative, so this is scored relatively to, suppose this is grade 4, then this is scored relatively to all grade 4 users that we have in the Netherlands. And they can zoom in on the graphs, and they can look at item level for each child to see what's happening, what's going wrong, to do error analysis, etc. Currently, we started with Maas Garden. That was the original thing. But then we made new systems, one for language, which is called Language C or Taalzee. We have an English system for learning English in Dutch elementary schools. Typing, blind typing, and one for statistics learning in psychology departments, and that's our most unpopular website. This is really relatively new, but Maas Garden, Language C, and typing are really going well. And And next month we start with a Danish version for Math Garden. This is the coverage in the Netherlands, so many schools use it. This is how it goes over the day. So this is 9:30 or 10 in the morning. Then children in the Netherlands make about 5,000 items per minute. This is my counter, so this is the speed of data inflow. As I said yesterday during dinner, if I'm unhappy when one of my papers is rejected, I can always go to my counter and look at my data inflow. Because that's quite fantastic. And this grows rapidly. So each year we have more schools. Currently we have, it's over there. We have about 1,600 schools using this system, and about 250,000 active users. So this is an incredible huge database. And it's also interesting that normally it doesn't. As I said in the beginning, if you want to go to schools and you want to do testing, that's really, really hard to, at least in the Netherlands, to get schools that want to host your research. But in this case, it's even the other way around. But because at some point, after 2 years, we decided to start a spin-off company and to sell the system to schools. So they have to pay for it, although they don't pay that much. They pay about €250 per child per year for each of the websites. But that's enough for me to build a little company and have programmers and maintain the system and build new systems. And it's cheap. They have to agree to allow me to use the data for scientific analysis. That's the deal. And the data are copied to one of our university servers, and people that work with me, or people that have a good plans, can use this data for scientific research. So that's the second part, what to do with all this data. Of course, the idea is that you have this educational system that's built with scientific ideas. Now we get back this data, and we like to have this cycle, and if that would work, that would be really promising. And we already have published a lot of papers about this system, although I'm still not satisfied. But I will say a little bit about it later. But the data is really easy to use for scientific research. So we have all kinds of papers. So many of the papers are just looking at some domain. So currently, last week I was working on a paper just about the clock reading task. So what makes clock reading hard? What are the item ratings? What's happening in all the grades? So you can already write papers for each of the tasks. Of course, you can also look at the relations between tasks, but we also write papers just about the statistics and the methods part of these systems and new developments. This is just for the overview, so if you want to look up papers, then you can do this here. So let's think a little bit about what you can do with this data. Of course, the interesting thing is that it's a field study. It's an ecological valid study. So this is what's really happening in the class. I go to schools and children do this all the time, or all the time. They do it a lot of time, but everything happened. There's lots of noise. So, I found children, the whole class is singing, have to sing a song, and then two are playing Math Garden and sing at the same time. Everything happens. And there are many domains, so it says here 34, but that's even more. So, and we have language games, math games, and games related to cognitive abilities. Incredible large sample size and age range, so 4-year-olds to adults, because isn't that the system? It looks, it's built for elementary school children, the way it looks, but the item bank is really advanced, so you can play it too, and you will see the multiplication gets harder and harder and harder at some point. There's no real end to the ability range. And we have this high frequent measurement. So some children do this daily and for multiple years. So that's a completely new window on development, as I call it. This is an example of a child playing the division game, and he plays it a lot. So this is just his data on one item, 21 divided by 3. And here you see the answers. This is the response time. These are weeks. And Q means question mark. So if the child has no idea of the answer, they can press question mark. And that's quite a popular answer, unfortunately. And he gives quick, this is a quick question mark, so he gets 21 divided by 3, no idea, question mark, quickly. But then sometimes the answer here was a good answer, so that's interesting, but maybe he got help. And then you see that at this point the correct answer gets in, but sometimes very slow, fast, so this is the real learning phase. And in here there's more or less a stabilization phase. So this is a child that really played a lot, so there are also children that come to a system, play 2 weeks, then they are lost for 5 months, and then they are back, just play a lot of games for some weeks. So it's very irregular, but this is the promise. This is the promise of what we can do with this type of data. But there are many issues too. I'm not going to discuss them all. Check my time. How much time I have?
You have about 20 minutes.
Okay. Yeah, I'm not going to handle there's a whole talk talking about all these issues, but one of course is privacy. So privacy. We make the data anonymously, use them anonymously, but still currently in the Netherlands there's lots of discussion about what we can do with this kind of data. And we have a privacy statement, we have a personal data protection act, we do lots of things to to safeguard our data, but it's an ongoing discussion about how to what we can do with this type of data. Of course, if we can use this data for scientific research, it's really huge. But currently in the Netherlands, it gets harder and harder to use data in this way. So I'm interested in how this works elsewhere in Europe. Now, the other thing is, of course, data integrity. If it's internet data, yeah, you can never be sure that all children have their own passwords, but things go wrong. So everything happens. And of course, we have the power of the sample size. We have so many children that we can easily exclude children, or whenever there's any doubt that something is wrong, we can exclude the data. But it's always a problem with internet data. Then data handling. If you have so many data points as we have, then it's quite a technical challenge to do the data analysis. Yeah, this is more a scientific point, that if you have such big data, new type of data, all your data analysis are mostly explorative data analysis. And that's quite tricky. It's easy to fool yourself. So you always have to find ways to check what you're doing. And normally what you can do, of course, is partition your data. So we have so much data that we can say, okay, we just take the data of January, we do all the analysis, and then we check it with February or March or whatever. But you always have to think about ways to see how robust your analysis are. And there are no real simple rules for this, so you always have to invent these rules for yourself and convince the reviewers and the readers of your papers that you checked all these results double, and that it's all really, there are stable results and not data fishing results. Okay, how do we know that this data is useful? Now, there are several ways. It's not so easy to do standard analysis. If you have an adaptive data set, that's a technical point, but if you know anything about this type of IRT analysis, and normally if you have a data set, then you have items, you have a matrix of items, and you have players or users, and this is a full matrix. That's a normal test. Every child might make one item. But here, if you order all the items in difficulty and order all the persons in ability, then all the data are on the diagonal because of the adaptive system. You only get items that fit your ability. So there's a huge amount of data on the diagonal, and off diagonal there's no data. So that's a very strange type of data. And many typical normal analysis that we do are not possible on this type of data. So we have to invent new methods. Not always. This is quite simple. This is just looking at the correlations of our ability ratings with the standard system that we have in the Netherlands to monitor children. This is the CITO system. CITO is the company in the Netherlands that does all the high-stake testing, and we compare the scores and we find quite high correlations. But in terms of reliability, you have to think about new ways. This is an interesting example. This is how item ratings go. So this is our items, and they develop over time, and you see how they move. And accidentally in this task we had double items. So some items, I don't know which items there are anyway, but they were just double in the item set. And that was not what we want, of course, but it gave a new way to test the whole system, because if there are double items, but they are independent items in the system, the ratings should develop in the same way. If the ratings of exactly the similar items would just diverge, then something is completely wrong. But we see always that these are two blue items, two red items, two green items, that they really develop in the same path. So this is a new way to look at the reliability. This is another way to think, to see what the data are. This is the ability growth per cohort. So these are our grade 3 children in 2009, that started in 2009. And these are the grade 3 children that started 1 year later. And if you do it in this way, this is the cohort 2009. And you see here the rating change over all the years that they were in the system. So this shows you, also a little bit about the amount of data that we have, but also the really stable patterns that we find, and that also encourage that this is really reliable and data. This is, for instance, the famous after holiday dip, after the summer holiday dip. Now, as I said, we can do lots of different things with this data, and we didn't explore all the possibilities, but one of the easiest things to do is domain analysis. As I said, we have the item ratings, lots of data, so you can just write papers about any of these games. And one example is, a famous example is multiplication. You have two multiplication games, one open questions, where they have to give the answer on a multiplication path, and one that's forced choice, 6 options, and the left one has 20 seconds, and the right one has only 8 seconds. So they are different, but we find very similar results. And this is the ability ratings per grade. As you see, this is grade 1 children, grade 2, and this is the ability ratings. And these are some example items, the positions of the items. So this gives you a rough idea of what's happening. Again, we see here that 100 times 3 is a simple item. They solved this already early in grade 2. And 8 times 7, famous item, of course, is really hard, and still hard for many children in grade 5 and grade 6. This is a way to look at to model the difficulties of the items. This is the first operand of the exercise or the item, and and in the picture there's the second one. So this is 5 times 1, that's 5 times 5, and on the y-axis you find the rating. And of course the table 1 is really easy. You can try to make statistical models to explain this data. This is the famous 9 effect. So the 9 table is a little bit easier than 8. This is the 5 effect. These are all effects described in the multiplication literature. But also interesting is the tie effect. So 2 times 2, 3 times 3, 4 times 4 are easier than non-tie exercises. So in the literature there are all kinds of predictors of item difficulty, and these are the main predictors, and if you just put them in a regression model, we can explain 90% of the variances in item ratings. And that's another way to check also results of the literature, find some new ideas, but also a check of the validity and reliability of our system. This is just published last year. Another example is our counting game. The counting game is a game for younger children, and they have to count fishes. So here we have to count 5 fishes, and then they have to click 5, and they have 20 seconds for that again. And this starts easy with 1, 2, 3, but it really gets hard. So we can still do it, because in the end you get something like 45 fishes in 20 seconds, and that's still hard. And there's an amazing amount of data on this. And we published a paper. It's not in press. This is an old sheet. This is 2014 or 13. on subitizing. So I don't know, some of you will know about subitizing. And the idea of subitizing is that counting until 3 or 4 is a different process than counting after 4. So just until 3, 4 we can just see, and afterwards we have to count. And people expect a switching, a different regression line in this part than in this part. And that's quite hard to study statistically. And this is a paper where we combined, by the way, this internet study with lab studies to make it stronger, and made a new point about the origin of subitizing. Another example is working memory. We have two working memory tasks. This working memory task is spatial working memory. So what they have is there's a grid of this grid, and then at some points this mole jumps up, and you have to remember where the moles are, and then you have to repeat the pattern, either forwards or backward. And this is also a popular task. For some reason children like to do this. I'm not sure why. And of course we have studied what makes working memory tasks exactly hard, what are the item ratings, can we explain the item ratings, but also how does playing the working memory game affect the math performance on other games. And there were really weak effects. So there were some effects that children that did practice the working memory task a lot played the math games a little bit better, but it was really, really small. That's also a problem with this type of data. You have so many data that you get easily statistical significant effects, and then you're really happy, and then you look at the size of the effects, and then you realize that it's not really much. This is another example. Deductive reasoning. This is a game, it's similar to the Mastermind game. Does everybody know what Mastermind is? Yes. It's a lovely game. Actually, we made it simpler. What we did is we only saw the last step. So there's that you already see all the steps, but the last step. So people, they see all the feedback on, say, 4 steps or 5 steps, and they just have to make the last part. That's a deductive part. And we made it not like this, but with flowers and all kinds. I don't have a picture. And that is really a reasoning task, deductive reasoning task. And with people in the logic department, they developed a logical model for this task, and we verified this model with our data. And we also found out that children use different strategies, or actually 2. The first strategy is not really a strategy. The first strategy is no understanding at all, so just random answers. But there were 2. One that has a limited type of conditional thinking, and you have the advanced players. And this is the ability distribution, and it's a really nice free modal distribution. Normally it's not so easy to find multimodality in distributions, but this was a really nice case. Now I can go on like this. There are many more papers on domains. This one that's just published today, I got this morning, is about this is a very simple game. So what the computer does, it pronounces a number, say 24, and then children have to type in 24. And in Dutch, that's a problem, because in Dutch we don't say 24, but we say 4 and 20. That's strange that we do this, but and that's trouble. And it's unclear how big this problem is for children, but it appears to be a big problem. And okay, it's the same in German and many other languages. In England, I heard that in England it was the same a long time ago. So about 150 years ago, 4 and 20 was also English. But at some point, you changed. Interestingly, because you didn't change some other things, but this you changed, and that was a wise decision, but because from our data it appears that it's really a big problem. The simple reversal of numbers and speech is a big thing for children. Another way to what we can do with the data, this was all about item ratings. Another way is to think about errors, because most of our questions are open questions. And then you get, it's not only they make a mistake, but they also make a typical escape. And for the popular games, you have thousands of answers for each of the items. And this is an example. So this is the question 9 times 9, and these are the incorrect answers. So the correct answer, of course, is huge, but I leave it out. So 18 is the most popular incorrect answer. And then 99, beautiful answer. 82, 91, 90. So this is the, and I forget about the lines for the moment. This is just a frequency distribution of errors in order. And actually explaining why it's 18 is not that simple. 5, okay, 5, good. Because there are different explanations. It could be an addition problem, so that they do just addition. It could be the famous Dutch problem, so instead of 81, they type in 180, 81. They just type it wrong because that's called the reverse error, and only not possible in English but possible in Dutch. And it could be a table-related error. This is the explanation from the literature. And it's hard to decide on basis of this item only, but if you combine all the items, scores for all children, you can make decisions on which error category is the most probable cause of 18 in this case. And I think it was addition. So what do you expect to be the most frequent error on 2 times 9? $19. So it's just one wrong. And then 16, 17. It's also interesting. This is 2 times 9. This is 9 times 2. And you see that the error categories are really the same. So that's another indication of the reliability of error analysis in this case. Another example is 6 times 7. In 6 times 7, the most popular error is 56. So here it is table related. It's an answer from a related table, not just one wrong. And one wrong is just over here. So here are the errors are much more related to the tables, but on the easier items they are just, we find one-off errors much more. Now, another thing that we do, as I said in the beginning, one of the big things that we now do in my department in Amsterdam is network modeling. That's the big thing. Network modeling of attitudes. We just had a paper in Psych Review. Psychopathology, but it all started with network modeling in intelligence. And one of the applications is do network modeling of all the games we now have. And it's not yet finished. We are working on this, but if we do put just all the ability ratings in a network analysis, you see a network for language, a network for the intelligence task, and a network, but all these networks are quite strongly related. So that's one of the things that we like to do here. Although I must say that doing the network analysis on this type of data is again tricky because of this strange organization of the data in an adaptive test. It's more complicated than I hoped. Things that can go wrong. I still have, okay, let's show something that can go wrong. Yeah, at some point in this small task, this working memory task, at some point the graphical people decided that we need a new layout. That's always dangerous. And as I said, there was a backward and a forward variant. So sometimes they get these moles and then it says, okay, you have to do it backwards, and sometimes you had to do it forwards. Originally that was very, very clear. So they know it was very clear that they do it. But in the new layout, these graphical people didn't understand this whole point, so they almost left out this instruction. It was only in language and it was very, very small. And then it did go wrong. So this is the rating development of people and items. So the colors are items, and the black are the persons. So there are a lot of persons. So most of the children are here in the black area here, and these are just items. These are very easy items because they just have one mole. So these are the most easy items. You see how stable they are. The red ones are the forward items, and the green ones are the backward items. Here was the new layout, and then suddenly a gap appeared between the backward and forward items, and it could not be recovered. I have no time to explain how this is a self-reinforcing effect. So as the gap grows, it will reinforce its effect, and it did go completely wrong. So this was just a small decision, and it had a big effect, and we had to reset the whole game completely after some time. Okay. Yeah, as I said, I'm not still. I still have big plans. So one of the things, if you think critically about my whole story, then you will see that I started about dynamics and about the idea of cognitive transitions and about individual data analysis. There's a new window on development. And because most of these papers that we all have are still about between-person effects and about the games, and still not much we have done on the dynamics of individuals. And there are 2 projects running right now, but we still don't have published results. So that's one of the big new steps. Another thing is to do more confirmative experiment within this system. So in commercial website world, it's called A/B testing. The A/B testing is just doing experiments, which means that you change certain things in your system and give them to random samples of your players, and then you can test effects of certain things in a confirmative way. One of the troubles is again this privacy thing. That in this case we have to get a new. We have to ask schools and teachers and parents again for agreement on this type of experiment. Now, my time is finished. I put on my plans and then we can have questions. Thank you.
I'm going to stand up here for the questions. Okay, we have about 10 minutes for questions, Han, and why don't we open the floor, and we also have the potential of some questions from Uvascula Dit. But we'll start with Manolis.
Yes.
Probably quick, but just thinking around the tasks, do you think that some of them have like multiple components? And
Yes.
How do you look at that? Like,
Yeah. No, this is a big thing. So it's in the end, it's required that all games are one-dimensional, like any test that we have. So one-dimensionality is a big thing, and it's really hard to decide whether it's really one-dimensional. And if you really are strict on this, then you have to make really narrow-range games, and you need a lot of games. But the problem with the backward-forward items in the working memory task is an example. So the decision we took in the end was to just get rid of all the forward items, because forward and backward items in a working memory task, it's just are more or less 2 tasks. So it cannot be in the same task. And these problems, the real cause of the problem was the fact that we mixed up 2 different abilities in one game. But on the other hand, you don't want too many games. If you make games for any separate ability, you get hundreds of games or thousands of games, and that's not useful for schools. So for instance, multiplication already, schools just want one multiplication game, but multiplication items that are in the tables, so 6 times 7, they just have to learn 6 times 7. But 15 times 3, for instance, in the Netherlands, you don't have to so that's an ability, and the other one, you have to it's retrieval. And retrieval and using backup strategies is not one and the same thing. So, maybe you should have a separate task for all the items that have to be learned by heart, the table-related items. But then, you go on and make more and more tasks. And then there are so many games, and then for children it's impractical to do all these games. So you have to find the balance here, and that's quite tricky. But it's always tricky for any task or test that we make.
Thank you very much for the presentation. Very interesting. I'm curious whether you've done any work looking at comparing this online work with paper-based work. A major problem I see, of course, is this we only have so much time, and this can be useful. Teachers like it because it's structured and available.
Mm-hmm.
Parents like it because the students look like they're engaged in using something, doing something, but you're taking them away from paper-based. Other kinds of interaction. Other mechanisms of learning. So have you done any work to see?
We did some work in terms of validity. So do the computer test measure the same thing as the paper test? But that's not what you mean. You mean no. It's the balance with paperwork and computer work in classrooms.
Yeah. Well,
yeah.
So paper study as well. I mean, a parent can just say, "Oh, go
Yeah.
Whereas
No.
it takes some time away from they're sitting at a desk interacting with the book.
Yeah, yeah. No, we didn't. And I must also say that schools in the Netherlands use this in very different ways. So we have some of these modern iPad schools, and they only use this. So all the children have to do about 8 games every day. And for some schools, they use it as an additional system, and it's just once a week, just more for the monitoring and not for the practicing. And there are all kinds of ways schools use this, and we also leave that to them, of course. That's up to them. And it's not really my field to do studies on this, because that's a completely different topic and a different expertise. But it will be really interesting to... the whole point of all these computerized methods in schools and how this relates to how we organize schools and manage schools and the role of the role of the teacher, that's very important. So this is one of the ideas. Oh, I don't know why it's... we like to have a system where children do or games, we do the analysis of what their weak and strong points are, and then we decide on instruction, and then we go back to practice. And the teacher is more or less monitoring. I don't know why this whole graph is mixed up, but that's a different position and a new role of the teachers, and that's all new. We have to investigate how this really works. But yeah, I think people that are in educational research that know about how to do these studies, they have to be involved. So this is really not my field of research.
Hola.
Thank you. Very interesting talk. And I'm happy to see the same kind of issues that we have in down here as well. I have lots of questions, but one of the issues, I might have missed this, but the items are ranked along the way. So do you have any issues with the teachers if the game goes a certain way and they have been introduced to material that they have not yet done in the
Yeah. In the beginning we had, but I must say the last 2-3 years I don't hear this anymore. But in the beginning we had 2 problems indeed. That one thing is that some children really go fast in this system. So they can just go on. So I didn't tell that if you start as a 4-year-old child, then you just get counting. And if you do counting well, at some point you get the addition game. And if you do that well, you get the subtraction and multiplication games. And there are children that are 5 years old. And they go so fast. They do the counting and they do the addition, and then they're 6-7 years old, and they do things that they have to learn in 2 or 3 years. And so they do the multiplication games. And in the beginning, some teachers asked to forbid this, to say, okay, you have to make the multiplication game unavailable for these children, because this is not what they do. But then it's also a big thing in the Netherlands, the whole discussion about adaptive, personalized instruction. So at this point they accept this and they find ways to help these children, and of course there's lots of other material, but it also depends a little bit on the school. As I said, we have about 1,600 schools. It's about 1/5 of the schools in the Netherlands. And there will also be schools that don't take our system just because of this. So I guess,
Okay, one last question. Lars, go ahead.
Okay, thank you. This is very interesting. Could you go back to the slide where you show the developmental trends from grade? This one with the rainbow colors. I'm just trying to visualize how complex the data is that really goes into that analysis. So you would have multiple entries for each child. So time points nested in. And then you would have children working on different games. So first the counting, and then the adding, and then the sum. So items in games in time. So this is very. How many lines would you then have each child, and how do you bring those together?
there are many different ways we organize the data, but the huge database we call the log file. The log file is just entries as they happen. So whenever a child gives an answer to an item, there's one new line in the log file. And the log file says just child number, item number, time of the day, rating of the child, rating of the item, answer, many other things, and then that adds on. This is this huge database that is now about 900 million records, and that's the basic. You cannot work with that database. That's so if you do, depending on the analysis that you do, you have to use certain SQL lines to get data in different ways, depending on the way you want to analyze the data. But for this, it's not that hard, because here, for this graph, we only need the abilities of the children over time. So for this graph, it's not that complicated, actually. But it can be really complicated, as you say. It can be, depending on what you do, there can be really complicated nesting structure in the data. Okay, thank you.
Thank you very much.